Hello and welcome to the course of Advanced Strength of Material. This is our 10th lecture. In the last lecture, we have discussed about eccentricity, eccentric load, and how the combination of the bending and direct stress is applied in case of eccentric loading. Now we will derive the combination of direct and the combined effect of bending and direct stress for the load when the load is subjected to a symmetrical section at an eccentricity with only one principal axis, that we will show. Here our lecture objective is to determine the effect of combined bending and direct stresses when the load is subjected to a symmetrical section such as rectangle at an eccentricity with only one principal axis. So this derivation will be in your syllabus, and we will see this one case. In the last lecture I have described about four four cases where this calculation, this direct and bending stress, both the stress are acting. Now we will see about the combination of bending and direct stress for the case of symmetrical section, and for the case of symmetrical section when the eccentricity is with the only one principal axis, that we will see. So we will see the derivation for that. So first, for derivation, we will consider a column of rectangular section which is subjected to eccentric loading P. You can see here that eccentric load is with respect to y axis. This is your y axis. This is your y axis here. With respect to this y axis, the point load P is acting. The line of action of the P is perpendicular to the normal, or perpendicular to this your cross section, and this D and B is the depth and breadth of the cross section. So now this eccentric load, due to this eccentric load P, that will cause direct and as well as bending stress, as we described in the last lecture, that whenever there is eccentric loading, that time both the direct stress and the bending stress, both the stress will be acting on the body. Now the combined value of the stress will be calculated through this derivation, and the maximum or minimum stress, maximum and minimum values of the stress will be calculated through this derivation. So that is our aim to calculate the combined value, or to identify the combined value, and to know about, or to derive the value of maximum and minimum values of the stress. So let's start. Let us assume that the P is our eccentric load. This P is our eccentric loading. E, this is deviation from the axis, deviation of the line of action from the axis, that is our eccentricity. Sigma 0 is our direct stress, sigma B is our bending stress. Now B is the width of the column, D is the depth of the column. Now by after knowing that, we can very easily we can derive the area. What will be the area? Area is nothing but depth into width, that we already know. So from this figure we can say the area will be B into D. That is our area, B into D. See here, the area is determined, that is B into D. Now the moment, what will be the value of this moment? What will be the moment for this force P? For this force P, which is eccentric load, the moment, in the previous lecture we have discussed, this eccentric load can be imagined by a load, or by eccentric load can be imagined by a couple. So moment of that couple will be nothing but force, that is P, value of the force, into load, or force or load into distance, that is E. That will be our moment. So value of the moment is nothing but load into distance, and that the value will be m is equal to P into E, that is our load into distance value. So now direct stress, this direct stress calculation is very easy. If the P load is acting on the body, at that time the body will at that time the body will create one the body will oppose that force, and by opposing that force, what will happen? By opposing that force, the value of the opposite force will be equal. Why? Because of Newton's third law. That this thing I am telling from the very beginning, that whenever a force is acting on a body, at that time equal and opposite reaction force will be generated, and that reaction force is normal to the area, and as that reaction force is normal to the area, the stress or direct stress will be nothing but the internal resistance per unit area, that is our P by A, or load by area. So and this will be that direct stress will be uniform, the direct stress will be uniform along the cross section of the column. So that is so the value of the direct stress we have got, simply we have got the value of the direct stress as P by A. So take this equation as equation number 1. Now we will see about the bending stress. Now bending stress, from the bending equation, in the last chapter we have discussed about this bending equation. So from the bending equation, what we know, the bending stress sigma B is a part of our flexural formula or bending equation, that is m by I is equal to sigma B by Y, where Y is the distance from y axis or distance from neutral axis. See, if this is our neutral axis, this is our neutral axis, so then the Y will be this distance. If this is our neutral axis, then Y will be this distance. So Y is our distance from neutral axis. And I, what is I? I is the moment of inertia of the rectangular section or moment of inertia of the cross section, of the given cross section where the whole calculation is based on. So the moment of inertia of the whole cross section about what? With respect to our neutral axis. That is our moment of inertia I. So we can write that sigma B is equal to plus minus m by I into Y. So from this equation we can write sigma B is equal to plus minus m by I into Y, where Y plus and minus is given if if the Y is above your x axis, above this axis, then it is your positive axis. This side is positive axis, this side is negative axis. So that's why m by I is given like this. Now the value of I for our rectangular case is nothing but b d cube by 12. This moment of inertia value we have derived in the previous semester. So we are here we will use directly the value of moment of inertia. Now if we substitute this moment of inertia value, well, if we substitute this moment of inertia value here, sorry, here it is wrong, because see b d cube by 12, when it will be like that, b d cube by 12, when we are calculating the value about x axis, whenever we are calculating the value about x axis, at that time the value will be b d cube by 12, where it is this side is our depth or d, and this size is b. But in this case we have to calculate the value of this axis y. We have to calculate the moment of inertia about y axis. So moment of inertia about y axis will be nothing but d b cube by 12. That will be our moment of inertia. Here a small mistake in typing occurs, so this will be not b d cube. Please note this. Okay, please note this. Here it will be db cube by 12. So moment of inertia will be db cube by 12. Now if we substitute this db cube by 12 along in the bending equation, that is here in the place of I. If we place dbq by 12, then the equation will look like sigma b is equal to plus minus m db by 12 into y, and that would be is equal to if we simplify it, that will be is equal to plus minus 12m by db cube. Now this bending stress, this is the bending stress which depends upon the value of y from the axis yy. Now that is the case. So in the throughout till now, what we have discussed, what we have known, we know that our first case from the direct stress, the value of the direct stress is m by I, and the value of the direct stress is m by I, and that value is uniform throughout the cross section. Now here we are getting the value of the bending stress, and that bending stress will vary from y that bending stress value depends upon the value of y from the axis, from the neutral axis yy. So bending stress at the extreme point, that means when the y is equal to b by 2, see here, here in this figure, when the y is equal to b by 2, that means at the point b, or at this section, or at this section, the value at this bc section, when it is point b at bc section, the value of y will be, the value of sigma b will be plus minus 12m db cube b cube into b by 2. Now if we simplify it, we will get plus minus 6m by db square. Now if we put the value of m, that is p into e, the value will be 6 pe db cube. Now db square. Now if we calculate further, or if we simplify further, we can write this b square as b into b. So here see, we write d b into b, that is our b square is equal to 6p into e by a. So see, d into b is nothing but area. Here d into b is nothing but area, so we can write 6p by a into e by b, where e is the eccentricity and b is the breadth. So from here we can see now this is our here sigma b equation, this is our equation 2. Now from this we can calculate, from these two we can calculate the direct stress and our bending stress. Now we can have the resultant stress at any point. The resultant stress at any point will be the resultant stress at any point will be the algebraic sum of the direct stress and the bending stress. So if y is taken positive on the same side of yy as the load, then the bending stress will be of the same type than the direct stress. Here direct stress is compressive, hence the bending stress is also will be compressive towards the right side of the yy. Now similarly, the bending stress will be tensile towards the left side. So taking the compressive stress as positive and tensile stress as negative, it can be, we can find the maximum and minimum stress at the extreme section. This stress will be maximum, the stress will be maximum along, see, the stress will be maximum along this section, stress will be maximum along bc section, and it will be minimum along ad section. So let's find out the value of maximum and minimum stress. So maximum stress, that is the stress along the section bc, that will be equal to sigma max, and sigma min is the minimum stress, that is the stress along ad. Then sigma max will be nothing but in case of bc, in case of section bc, we can say that the bending stress, so section bc means this section, so here the bending moment in this side, so the bending stress and the this compressive stress, this will be the same in nature. So that's why they they are added together. So the sigma max is equal to sigma 0 plus sigma b, or direct stress plus your bending stress, and the value will be, if we put the value, that is P by A plus 6 PE into A by PE by A into B. Now if we take the common P by A, then we will got sigma max is equal to P by A whole bracket 1 plus 6 E by B. That is our value here in the sigma max. This is our sigma max value. And again, the sigma mean value is direct stress minus bending stress, because here the bending will be in this direction, because bending is complementary, because here the direct stress is always in this direction. So here the bending moment will be minus, and the value is P by A 1 minus 6E by B. So these stress are shown in this figure, and this figure will known as combined stress distribution figure. Combined stress distribution figure. So the resultant along the width of the column may vary by a straight line law. So from this figure we can say that the effect of the combined stress may vary through a straight line. And in the equation sigma mean is negative, then the stress along AD will be tensile, and if sigma mean is 0, then there will be no tensile stress along the width of the column. If the sigma mean is positive, then there will only be compressive strength along the width of the column. So with this we can end our derivation. Thank you. Hope you understand this derivation. We will derive it in the live class also. So please, if you have any problem, then please ask me in the live class. Thank you.